Sergey Goryainov. He will present some new results. So the floor is yours, Sergey.
Thank you very much. The title of my talk is Tightness of the Weight Distribution Bound for some stronger regular graphs. And this talk is based on joint work in progress with Leonid Shalaganov. Let gamma be a k-regular graph on n vertices and theta be an eigenvalue of its adjacency matrix A. Let U be an eigenvector of A corresponding to theta. Then U defines a function fu on the vertices of gamma with real values such that, okay, this function is called a theta eigenfunction of gamma. So there is just one-to-one correspondence between eigenvectors and eigenfunctions. For an eigenfunction fu of gamma, the support is the set of all vertices in this graph such that the value of the eigenfunction on these vertices is non-zero. The following problem was first formulated by Vorobyov and Krotov, and see also a recent survey by Sotnikov and Volozhenich for the motivation and details. So problem one called a MS problem. The MS problem, given a graph gamma and its eigenvalue theta, find the minimum cardinality of the support of a theta eigenfunction of gamma. So the abbreviation MS means minimum support. A theta eigenfunction having the minimum cardinality of support is called optimal. And let us consider the second problem. Given a graph gamma and its eigenvalue theta, characterize optimal theta eigenfunctions of gamma. Let us make a survey on problem 2. Recently, problem 2 was solved for several classes of graphs. All eigenvalues of Hamming graphs when Hamming graphs H and Q when Q is equal to 2 or Q is greater than 4, and some eigenvalues of the Hamming graphs H and Q when Q is equal to 3 or 4. All eigenvalues of Johnson graphs asymptotically, the smallest eigenvalue of Hamming, Johnson, and Grassmann graphs, the largest non-principal eigenvalue of a star graph Sn when n is greater or equal to 8, and the largest non-principal eigenvalue of Du graphs. Accepting the results from the previous slide, problem 1 was solved for several more classes of graphs, both non-principal eigenvalues of Paley graphs of square order and stronger regular bilinear forms graphs over a prime field. Let us discuss the weight distribution bound. Let gamma be a distance regular graph of diameter d with the following intersection array. For an eigenvalue theta of gamma, the following bound was proposed in 3, corollary 1. A theta eigenfunction f of gamma has at least the sum of absolute values of wi's non-zeros, where w0 is equal to 1, w1 is equal to theta, and wi can be computed recursively using the previous two values, the eigenvalue theta and the parameters from the intersection array. Let us survey some known results when the weight distribution bound is tight. The eigenvalue -1 of the Boolean Hamming graph of an odd dimension and the minimum eigenvalue of an arbitrary Hamming graph, both non-principal eigenvalues of Paley graphs of square order, the minimum eigenvalue of Johnson graphs, the minimum eigenvalue of Grassmann graphs, and the minimum eigenvalue of stronger regular bilinear forms graphs over a prime field. It was shown in 3 by Krotov, McGinnis, and Potapov that for the smallest eigenvalue of a distance regular graph gamma, the tightness of the weight distribution bound is equivalent to the existence of an isometric bipartite distance regular induced subgraph T0 joined with T1, where T0 and T1 are parts, such that an optimal eigenfunction up to multiplication by a non-zero constant has the following form: f of x is equal to 1 if x belongs to one part, f of x is equal to -1 if x belongs to the other part, and 0 otherwise. If gamma is a strongly regular graph with non-principal eigenvalues R and S, where S is less than 0 and R is greater than 0, the following holds. So this is the application of the weight distribution bound for strongly regular graphs. And as eigenfunction f of gamma has at least -2s non-zeros, and the cardinality of support of f meets the bound if and only if there exists an induced complete bipartite subgraph with parts T0, T1 of size -s. And for the positive non-principal eigenvalue R, and R eigenfunction f of gamma has at least 2 times R plus 1 non-zeros, and the cardinality of support of f meets the bound if and only if there exists an induced disjoint union of 2 cliques T0, T1 of size R plus 1. In 4, together with my colleagues, for Paley graphs of square order, we show the tightness of the weight distribution bound for both non-principal eigenvalues, which can be computed by these formulas. Let me make some remarks on this result. Let beta be a primitive element in FQ square. Let omega be beta in Q minus 1. Then the subgroup generated by omega is the subgroup of order Q plus 1 in the multiplicative group of the finite field. And here are some facts about Q. Q is an oval in the corresponding affine plane. Q is the kernel of the norm mapping, which means that Q is the set of solutions of this equation gamma to Q plus 1 equals 1, or equivalently, Q is the set of all elements x plus y alpha, where x and y are from the subfield of Q, and x squared minus y squared d equals 1, where d is a non-square in the multiplicative group of the subfield, and alpha square is d. So Q can be viewed as the set of solutions of an analog of Pell's equation, but for finite fields. So we observed these properties of Q, and also we considered the subgroup of index 2 in Q. Let Q0 denote this subgroup, and let Q1 denote the other coset. Here are 2 more facts about Q. If Q is congruent to 1 modulo 4, then Q0 and Q1 induces a complete bipartite graph with parts Q0 and Q1 of size Q plus 1 over 2. And if Q is congruent to 3 modulo 4, then Q0 joined with Q1 induces a pair of disjoint cliques Q0 and Q1. So it means that we have found an embedding of certain subgraphs. So the weight distribution bound is tight for both non-principal eigenvalues of Paley graphs of square order. And knowing the structure of Q, we were also able to construct new maximal cliques of the second largest known size in Paley graphs of square order. See our paper 4 for more details. So looking for eigenfunctions having the minimum cardinality of support, we have found some additional maximal cliques. And recently, we had a look at generalized Paley graphs of square order. Let m be a positive integer, m greater than 1. Let q be an odd prime power. Q is congruent to 1 modulo 2m. The m Paley graph on fq, denoted by gpqm, is the Cayley graph on the additive group of the finite field with the connection set consisting of all m powers in fq star. We consider the generalized Paley graphs of square order gpq square m, where q is an odd prime power and m divides q plus 1. These graphs are strongly regular and form a generalization of Paley graphs of square order. The usual Paley graphs of square order are just two Paley graphs of square order. And the eigenvalues of these strongly regular graphs, so in the case when m divides q plus 1, are as follows: s is equal to minus q plus 1 over m, and r is equal to m minus 1 q minus 1 over m. And given an odd prime power q and an integer m greater than 1, such that m divides q plus 1, minus q plus 1 over m eigenfunction of the generalized Paley graph has at least 2 times q plus 1 over m non-zeros. This is given by the weight distribution bound. Let us divide q into m parts. So in the previous case of usual Paley graphs, we divided q into 2 parts. So now we generalize this approach where so the parts are q0, q1, so on qm minus 1, where q0 is the subgroup of index m in q, and q1, so on qm minus 1 are the cosets. Here are 2 useful lemmas. Let q, the first lemma 2 can be used to test if an element of the finite field is an mth power. Let q be a prime power and m be an integer such that m is greater than 1 and m divides q plus 1. The mapping gamma to gamma in q minus 1 is a homomorphism from fq square star to q. Moreover, an element gamma is an nth power in fq square star if and only if its image gamma in q minus 1 is an nth power in the subgroup q. And the second, lemma 3 gives an important condition which combines the additive and the addition and multiplication operations. So we think this is an important condition for the structure theory of finite fields. Let gamma be an arbitrary element of q and gamma is not equal to 1, then the image of the element gamma minus 1 under the action of the homomorphism is minus 1 over gamma. So we start with a difference and get an expression in terms of gamma. So using these lemmas, we proved a theorem. So the following theorem basically states that each of the sets Q0, Q1, Q minus 1 induces either a clique or an independent set, and there are at most two cliques among them. Moreover, the following theorem, which is on the next slides, states that for every independent set Qi1, there exists uniquely determined independent set Qi2 among Q0, Q1, Qm-1, such that there are all possible edges between Qi1 and Qi2, and there are no edges between Qi1 and Qi2. So the formulation of the theorem is very long and deals with several cases. I will just skip it because I have explained the main meaning of the theorem. So it takes 4 slides to write down this theorem. And as a corollary, we get the following: let Q be an odd prime power and M be an integer M greater than 1 or greater or equal to 2, M divides Q plus 1, then, except for the case M equals 2 and 2 divides Q plus 1 over 2, there is at least one pair Qi1, Qi2 among Q0, so on Qm-1, such that Qi1, Qi2 induces a complete bipartite subgraph, which means that the weight distribution bound is tight for the smallest eigenvalue minus Q plus 1 over M for the generalized Paley graph. And in the rest of my talk, I will focus on strongly regular graphs related to polar spaces. These are affine polar graphs VO plus, affine polar graphs VO minus, orthogonal graphs O2E plus 1Q, O plus 2EQ, and O minus 2EQ, symplectic graphs 2EQ, and unitary graphs U and Q. For each of these families of strongly regular graphs, we show the tightness of the weight distribution bound for the positive non-principal eigenvalue R by constructing a pair of induced isolated cliques of size R plus 1. The definitions, I will recall some definitions and present the construction of the cliques. Some of these cases are quite straightforward, and let us consider two cases in more details. The first one is affine polar graphs VO plus 2EQ. Let V be a 2E dimensional vector space over a finite field FQ, where E is at least 2 and Q is a prime power, provided with the hyperbolic quadratic form. The set Q plus of zeros of the form is called the hyperbolic quadric, where E is the maximal dimension of a subspace in Q plus. A generator of Q plus is a subspace of maximal dimension E in Q plus. And the following lemma states that given an E minus 1 dimensional subspace W in Q plus, there are precisely 2 generators that contain W. Note that this lemma was used to construct strictly Neumayer graphs in our paper with Evans and Panasenko. Denote by VO plus the graph on V with 2 vectors X and Y being adjacent if and only if the value of the form on their difference is 0. This graph is known as an affine polar graph. And this affine polar graph is a vertex transitive strong regular graph with parameters given on the slide, and we are interested in the positive non-principal eigenvalue, which is q in E minus q in E minus 1 minus 1. Note that this graph is isomorphic to the graph defined on the set of all 2 times E matrices over Fq of the following form, where 2 matrices are adjacent if and only if the scalar product of the first and the second rows of their difference is equal to 0. And 2 more lemmas from the book by Bart de Bruyn. There is a one-to-one correspondence between cosets of generators of Q plus and maximal clicks in these affine polar graphs, and every maximal click in such an affine polar graph is a Q in E minus 1 regular, Q in E click. So in view, let us present a construction of an optimal eigenfunction of such an affine polar graph corresponding to its positive non-principal eigenvalue. In view of lemmas 1 and 5, such an optimal eigenfunction, if it meets the weight distribution bound, is given by a pair of disjoint cliques of size q in E minus q in E minus 1, and the cardinality of support is 2 times this difference. Take the following E minus 1 dimensional subspace, where the stars means that we take all elements, all admissible elements in these entries. According to lemma 4, this subspace is contained in exactly 2 generators. These are W0 and W1. It can be easily checked. And so basically we have taken 2 generators with maximal intersection. The intersection is a E minus 1 dimensional subspace. And let us consider, okay, the cliques W0 and W1 are Q in E minus 1 regular and have Q in E minus 1 vertices in common. So the sets W0 minus W and W1 minus W induce a pair of disjoint cliques of size Q in E minus QE minus 1, which means that the weight distribution bound is tight for the eigenvalue R. And in the same manner, we consider the other family of affine polar graphs, and the eigenvalue will be Q in E minus 1 minus 1, which is also an eigenvalue of several more strongly regular graphs related to polar spaces. In a similar way, but not exactly the same, we get a construction of 2 induced isolated cliques of certain size, which proves the tightness of the weight distribution bound. We also consider graphs on isotropic one-dimensional subspaces of vector spaces provided with parabolic, elliptic, and hyperbolic quadrics, and the eigenvalue is the same, and we just construct just construct appropriate cliques. And let me focus on the last family of graphs, which is the family of unitary graphs. Let V be an n-dimensional vector space over a finite field Fq, where Q is a square. The Hermitian form on V is the mapping given by this formula. So we consider the sum of products of coordinates of two vectors, where the coordinates of the first vector taken by themselves, and the second coordinate is taken in the power square root of Q, which is the action of the automorphism of order 2. The vector x of V is called isotropic if the product, the Hermitian product of x with itself is equal to 0. A subspace in V is called isotropic if every vector in this subspace is isotropic. Denote by UN of Q the graph whose vertices are all isotropic one-dimensional subspaces on V with two vertices given by the one-dimensional subspaces for vectors x and y, B and JSON, whenever one of the following two equivalent conditions holds. The first condition is the Hermitian product of these two vectors is equal to 0, and the second condition is the two-dimensional subspace, including these two fixed one-dimensional subspaces, is isotropic. This graph is known as a vertex transitive strongly regular graph, and if we take n to be equal to 2e, then we have the following set of parameters. If we let us know that the eigenvalue is q in e-1 minus 1, and if we consider the case 2e plus 1, we give a strongly regular graph with some other parameters, but in terms of e, the eigenvalue r will be the same. And let me conclude my talk with two constructions of optimal q in e-1 minus 1 eigenfunctions of unitary graphs. Let us start with the case of odd q. Let beta be a primitive element in Fq, and let gamma be the element beta in square root of q minus 1 over 2, which means that gamma in square root of q plus 1 is minus 1. And consider the following sets of vertices. Let V be the set of all one-dimensional subspaces given by the vectors, and we repeat coordinates in some sense. So we take V1 and V1 gamma, V3 gamma, and so on. But the last two coordinates are gamma and 1. So we have three braces, which mean that we first take a vector, then we take the one-dimensional subspace given by this vector, and then we consider the set of all such one-dimensional subspaces. In the same manner, we deal with the case when n equals 2e plus 1, and consider the following sets of vertices, which are just extension of the previous sets by the last coordinate, which is equal to 0. In all cases, v1, v3, v2, e minus 3 run over Fq independently, and it can be checked by by the definition of the product and by the definition of the unitary graph, that the sets V0, V1 induce a pair of disjoint cliques of the size Q in E-1, which means that the weight distribution bound is tight for the unitary graph in the case of odd Q. And a different construction, this is the last slide, a different construction was proposed in the case of even Q, which is a little bit different from the previous one, but the main idea is the same. We just repeat some coordinates. And it would be interesting to solve problem 2 for these eigenvalues and characterize the eigenfunctions having the minimum cardinality of support, which is equal to the value given by the weight distribution bound. Thank you for your attention.
Thank you very much, Sergey, for the interesting talk. Are there any questions to Sergey? Well, if not, then let us thank Sergey again for this nice talk, and we are looking forward to read the manuscript containing all of these interesting results. Thank you very much. And I also would like to thank all our